this is a great resource to have to go back to refer to your class. Has everyone used Tegrity before? No? Okay. You could make it to class. You could actually connect in live to the class, and what you will see is the screen, whatever screen I'm on. Now, my whole presentation isn't really screen focused, so those are the parts that you would miss a little bit, but you would hear audio continuously. It's worth learning about a little bit. You can download the class to your iPhone, to a podcast. You can just listen to it when you're driving. You can do whatever. It's pretty useful stuff. So it'll be there when you go into Angel, and you'll go into your Tegrity video recordings, and you'll see them there. Now, I did check it out. I asked about switching to Canvas, and since it's late in the quarter, you haven't paid for it is the problem. If everyone in the class wants that, then you can pay for it, and it's like another $25. I don't really see the need for it, honestly, with what we have. We can use the gradebook. I can publish Tegrity videos, and for the days that I'm not here, you can see the video for the class. I will do a special video of class, and that will be class. So you're going to watch the video from wherever you are, and you'll have your assignments there and things to do there. I have not decided what to do about the exam that I scheduled for the day that I'm not going to be here. So I'm going to figure that out. I'm not sure, and I'll talk to you about it. So that's a logistical update. So we're just going to stay with Angel. I don't think it's that worth so much to go over to Canvas since this is an in-person class. And Angel will have all your grades posted when you get something accomplished. It'll go up on Angel, and these videos will be there as well. Okay. All right, great. So now let me show you another resource that I'll be using because I just don't. This book didn't. I'm going to use some other resources, but go along the content of this book. Okay. So you're going to do the homeworks in the book, but I'm going to use a PowerPoint from another source, and those PowerPoints you can find at this website over here. And I'm going to show you this website because I'm going to refer to it a lot. This is Pierce's website at the heart of it. So there's Pierce's website. That's pierce.ctc.edu. Okay? So if you just Googled Pierce College, Steilacoom, or whatever, Washington, you would get to this website eventually. If you just go right on the end of this address and type go/chemistry. Go/chemistry. I'll put this link up on Angel also for you so you have it available if you forget it. But I'm just showing it to you now. So go chemistry, and that's going to take you to a hokey chemistry site that our lab guy over there made. But it's worth it because it's a place where you can put some stuff up, So if you go here to chemistry instructor and class websites, you'll see all different instructors, and here's me. So Chem 100 is the equivalent of 110 over there. So this is Chem 100. And if you go in there, you'll see PowerPoint. So I'm going to use this PowerPoint right here, and I'll have other ones up there as the quarter goes along because I am teaching this class over there also. And I'm going to do a lot of congruent things in both schools. So there will be worksheets and practice problems and things posted here that are available to you as well that I'll refer to. So it's where a lot of the practice work I have is available online. Okay? Yeah.
The chapters for this website do not correspond with that.
No, they don't. Yeah. Like today I'm going to start. You don't have anything in your book on the scientific method, but you need to learn the scientific method. So we're going to do that out of this chapter. And then I think they made a mistake, honestly, with this book. I think they ordered it by accident. I think someone made a really bad choice because it's kind of like a chemistry magazine. It doesn't really go into any detail, so that's another reason to get your information from class. This does not go into any detail about stuff. So I will go into detail. I'll teach you about all the different things, but there's something up with this book. I just don't understand why they chose it. And it's like a new book, so someone had a bad day, I think. I don't know what that was. And I haven't been teaching chemistry a lot long, but I know that that's not a good book. So So anyway, so I guess it's nice to kind of touch the surface of things, and then the professor can go into deep, like more depth about it. So that's what we're going to do. All right. I should be saying those things while I'm being recorded, should I? That's stupid. Sorry. But yeah, I know. But maybe you don't need to hear it. That's the point. All right. So that's that website. Great. Here we go. We're going to reduce that. Now, so today in lab, you're going to have the opportunity to practice this method, the scientific method. So I just wanted to lay it out a little bit with you first. Okay, so any of these problems or discoveries that have created this world that we have, from vitamin C to penicillin to T-shirts to sneakers to whatever we use that is part of the developed world, has been accomplished through some method regarding the scientific method. So there's a problem, right? There's some problem or some question that needs to be answered. And then you pose a series of possible solutions. Science refers to this as making a hypothesis. So hypothesis is a proposed solution. So let's say I have a problem. I have let's say the class, my problem is the class isn't learning. And I propose that I say, well, you know, if we get a better book and we have more frequent outcome quizzes, like see if they're actually learning something more frequently, that will help increase the score. That's a hypothesis. I haven't tested it. It's testable, but it's just a suggestion. It's like it's a possible solution. I don't know if it's going to work. Okay? So then the person decides which way to proceed to solve the problem. You decide, and then you go and you do an experiment to see if you solve it. Okay? So that's like a very overall, a bird's eye view of it. So now the scientific method is laid out in a couple steps here, in 4 steps. So first is you collect the facts or data relevant to the problem. So this is done with carefully designed observations and experimentation. So observations are a key part of the scientific method. If I say that when I heated it to 50 degrees, it turned blue, that's an observation. That's not a hypothesis. It's not a problem. It's not a question. It's just an observation. You make no judgment of it. It's just an observation. So that's a very clear step and ingredient in the scientific method is to observe through experimentation. When I do this, this happens. When I do this, this happens. That's the kind of thing that you're going to be looking for. So when I speak loud, more people hear me. You know, so these are observations that I have. When I speak loud, when I speak in monotone voices, people don't listen to me as much. It's an observation I have. When I'm tired and not wanting to be here, I'm a drag. Observation. Just an observation. It's not the truth. I'm making up something that is about you. I don't know what you want. I don't know I don't know how you are thinking of me. I'm observing it because I saw one person's face look like they were out of it, you know? So these are observations. So a very clear distinction is an observation. And in science, you're going to observe different behaviors. I observed that the liquid bubbled at 100 degrees. I wonder what it was. It's probably water, right? Okay. Then you formulate a hypothesis that accounts for the data and that can be tested further. So a hypothesis is something that can be tested. Okay, so you want it to be able to be tested when you generate a hypothesis. You don't want to have outlandish hypotheses that can't be tested. That's like, you know, or an example of a non-hypothesis is is the reason is the sky is blue because children dream. You know? I mean, it sounds cool. But how would you test that? You know, where do you tie it? I don't know of any connection between dreams and atmosphere yet. If there were some sort of connection between dreams and atmosphere and the weather, maybe that would be testable. But maybe there is testable. Now I'm thinking about it. Maybe that is testable. You know, but you see what I'm saying? It's like I just went out there and tried to pick something that I didn't think was testable, but now I'm thinking, well, maybe I can make a test like that. But something that's just not testable, you can't formulate a hypothesis on it. Okay? But that would have been a hypothesis if it was testable. Okay? I could say a hypothesis for something about boiling points would be when I mix two different organic chemicals of differing boiling points, the one with the higher boiling point becomes the boiling point of the mixture. That's what I think happens. Why? Because of the secondary forces. And then I would test it. And I could test it with all different mixtures. So that's a question, and then I can go and do an actual experiment on it. Okay, so then you plan and do additional experiments to test the hypothesis. So now you're in the world of, well, what is it? How am I going to test it? And then verify the results. And if the results don't give you what you want, then you got to go back and change the test a little bit to get the results that are going to prove what you're trying to prove. So you learn while you're doing the testing, right? So you might, while you're doing the testing, realize, oh, I need more data. I need to, if I was going to say, women over 30 do better in this class. If that was my observation, and then I built off of that observation because I've seen it. I've seen every person over 30 do better in this class than anyone younger. Then I would say, well, that would be my hypothesis. Women over 30 do better in this class. And then I could do an experiment. So then I'd say, well, all right, next class I have, I'm going to interview everybody. I'm going to see how old they are. I'm going to see where they're at in their life. And I'm going to say, okay, look, I'm just doing this experiment. And I just want you to know I'm going to use you for data. Are you good with that? Okay, yeah, great. And then sure enough, everyone over 30 does better than everyone. But then there's just like two younger people who blow the whole class away, and they're like much better. So I'm like, all right, that didn't work. What was special about them? So now I'm going to look at it again. Well, I didn't prove it. But was the majority? All right, I have to reduce the number. I need to. So I'm trying it. Why do I really want to know this? What do I want to use this information for? Okay, so I'm having this dialogue with myself or with somebody else, hopefully, and trying to figure out how to demonstrate some distinction I have that mature people who I think are over 30 are doing better in the class because they're more focused on the class. Or I could say students who return to school do better than students who are in school for the first time who are getting paid, who are having their way paid for. Like, that's an observation I've had. I was one of them. So I think that would be true. And I think that's true because they have to work for it, they know the value of it, and they're going to apply it. Most of the time they're in a job right now that they can immediately apply what they're learning to, and they get the value of education. How would I prove that? I'd have to do a survey. I'd have to get a population. I'd have to go to other schools. I'd have to create a whole experiment to generate data. And would it be true if I proved that it was true? No. It wouldn't be true. It would be a theory. I proved a hypothesis. I've demonstrated with a lot of data that the hypothesis was repeatable, that it was actually good information. So now I have a theory. Once your hypothesis has been proven many times through experimentation, reliably proven, like pretty much 9 out of 10 times, you're going to have the same results no matter where you are. Now you've generated a theory. And that theory then can get published and then people use it. But it's a theory. So a lot of the things you're going to learn about are theories. They're based on theories. We did this experiment today in class, and Pierce has this little this box that's an experiment. It's a closed brown box, a wooden box, and 20 years ago, somebody made these boxes, or they bought them. I don't know where they got them from. But inside is like different dividers, or a spring, or a marble, or a BB, or something mixed in there with certain pathways. So when you move the box around, the ball will like travel, and then it'll hit a wall, and then it has to go right and left to get around the wall. So their job is to tell me what is in the box using the scientific method. So the whole class is shaking the boxes around and moving. Sounds like a ball. Okay. It's a ball. Well, what size is the ball? What material do you think it is? Well, how would we know what material it is? So you keep asking questions and keep experimenting to figure out more information. Ask questions, experiment, until they come up with more information. And by the time they submitted the results to me and I told them they were wrong, they're like, no way. No, that's not true, because they've convinced themselves that that's what's in there. And then the question was, well, go back now, and now that you know what it is, experience what it is that it's telling you. Like if it's a spring, I want you to feel that there's a spring in there, and find some way to identify that there's a spring in there. Maybe by the sound, or by shaking it and hearing it go wing, 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 wing. You know, whatever it is, find your way to say, yeah, that's a spring. That's true. Then go back to your experiment and think about what step you could have included that would have identified that. So that just shows how much there is to discovering something that you can't see, and how much error is possible too in these theories. That's why the theories keep changing. The theory of the atom originally was that electrons orbited in predictable patterns. There was this theory. The original theory of the atom was that there was a nucleus and that there were electrons, right? And that there are these orbits. Everybody probably remembers this looking thing, this thing like that, right? And the electrons went around the orbits, and they stayed in these orbits, and they were single electrons or two electrons in orbits. And they would have to do these leaps to go into different energy levels. Now they understand that there is a nucleus, that's sure, there is a nucleus, everyone knows there's a nucleus, but there's electron clouds. And the electrons are not in these circling in these orbitals, but they are contained in certain shells. But it's more of a cloud. And this, what I'm showing you, is one electron everywhere at once. It's kind of, but very fast. So the location of the electron is now known to be based on a probability factor. It's probably located inside here, but it is not 100% definitely located here. The theory of the atom changed. They used to think that it was in orbitals based on the experiments they did, because they can't see in there. So they're looking inside this box trying to figure it out. So there's always this other place where you can't really see or understand, and you're developing theories about what it is. That's the frontier of science. So it's just one example of how it changed, and you'll see this in this is what I was saying, that when you observe it, it changes location. It is so sensitive and it is so everywhere. It's kind of like a fuzzy TV. You know, the white noise. That's what an electron's like now. That's what they understand an electron to be like. So it's just this all over here. There might be two electrons here, but they're just bouncing around. So they're not actually in this perfect little orbit like they thought that there's like planets revolve around the sun. All right. So a clear colorless liquid is combined with a second clear colorless liquid, and the mixture is observed. Which of these is not an observation? Which is not an observation? Raise your hand. What's your name? Tammy. B. B is not an observation. Why? Well, first of all, you probably don't even know what exothermic is, so that would be a good So if you can't observe it, you can't observe something you don't know it is. But exothermic is a type of chemical reaction. It's a classification of a reaction. So it's not something you observe. It's something that you would know and you would have to check with temperature. So it's simply, the others are very clear observations. The tube is hot, the mixture is cloudy, the mixture is white, but the reaction is exothermic is a chemical classification. It's not something you observe. Okay. So, when you have your observations, you are going to analyze them, right? And they will become hypothesis. The hypothesis is then experimented, and then through the experiments you get new observations. So it loops back around. One moment. So this little feedback loop happens. Through experiment, you make new observations, you generate new hypothesis. Through experiment, you make new observations, you generate new hypothesis. Through experiment, you generate new observations, and so on. And it goes around and around until you've come up with a consistent result. Once you've done it enough times, and you've said, okay, now I've experimented this time, I've experimented with this variable, I am very confident that this is what will always happen. Now you've generated a theory or a model. Right?
It's a lot.
What's that? That's a lot, yeah.
Is it a lot?
Is it a lot to do that?
A law.
Oh, it's not a law if it's a theory.
So what is a law?
So a law is a statement of natural phenomena to which there are no known exceptions. So there is no, it's a natural phenomena, like gravity is a law. There are no exceptions to the law of gravity on planet Earth. On Earth, there's a gravitational pull. It's 9.8 meters per second squared. There's no question that that is how things occur. Another law is like Boyle's law for gases. When you heat up a gas, it expands. That's a law. It's a natural phenomena that is clearly observed, that is irrefutable. They are laws of the universe or laws of the planet, laws of the earth, of how this earth operates. It's a law. So they're irrefutable. They're very testable, but they're irrefutable. That's just how it works here. Of course, there are people that challenge that and say, well, that what if, the world used to be flat? And, but you see, that wasn't a natural phenomena. Nobody saw that. That was just speculated, that there must be some end somewhere. So a law is observed, it's calculated, and it's irrefutable. It's just what it is. Under all conditions, and it's very well understood. So you can look at the Boyle's gas law and heat up any gas. Any gas will expand if you heat it. It will get bigger. It will expand in volume. If you heat up your balloon, right? If a hot air, anything hot, if you heat up water, right, it gets bigger. Kinetic energy has things get larger. Those are natural laws. So that's when something is a law. All right. A theory is a well-tested hypothesis and is always up to change. If someone can demonstrate that, they would go through the scientific method, experiment. Their hypothesis would be that the theory is wrong, and and then pose their reason why it's wrong, and then go through the whole loop until they can demonstrate a new theory. All right, which of these is laws? So here you get a practice to consider laws. Atoms consist of protons, neutrons, and electrons. All matter is composed of atoms. I think I just told it to you. Atoms can form chemical bonds by sharing electrons, and volume of gas increases with increasing temperature. So D, obviously. Shouldn't have used that example. But look at it. Let's just look at it. I was just telling you that these are theories, right? So what's known about the subatomic world is all theory. It's all based on theory. So atoms consist of protons, neutrons, and electrons. It's true, we're working with that, but it's all based on the atomic theory. It's still theory. All matter is composed of atoms is theory. But that was part of the atomic theory, that everything is made of atoms. Yes, it's been tested, it's been demonstrated, but it's not a law. Atoms can form chemical bonds by sharing electrons. That's true also. That's what we're teaching you based on that theory, but it is all theory. All right. A statement. An atom consists of dense nucleus surrounded by a cloud of electrons is an example of what? A theory, a law, a hypothesis, or an observation? Who had an answer? You say theory? Anyone else? We got one for theory. Theory. One for hypothesis. Observation? Who wants to put their name by the answer? How do you say your name? D-E-E? We'll just do the D-E-E, is that right? Can I just put D-E-E? Okay. Anyone else want to?
Well, I guess you just told us that it was tested, because that's the new way of thinking about it. So it is a theory. But if it hadn't been tested,
Well, a hypothesis is almost like a question. It's generating an idea and suggesting something. This is actually saying an atom consists of dense nucleus surrounded by a cloud of electrons. It has nothing. Where's the example of the hypothesis that we had? Counselor, a tentative explanation of the facts that can be tested further. That's not a tentative explanation of facts. It's just telling you how something is.
It starts as an observation.
Yes, it would have started as an observation, yeah. All right. Now we've looked at all this stuff, right? Everyone remember this? We did all this, yes. We did all this last time. Okay, so now we're going to jump over. And while we're on this, I'm going to go ahead and look at your lab prep for a minute. Those of you who have questions about the pre-lab, what? Come on now. I don't understand. Maybe not a couple. That's my password. I'm sorry about the fact that you can't know my password. That's just crazy. I'm in here. Why won't you let me see my stuff? Arr. One more try. All right. The syllabus, yeah. You do, but I wanted to put it up there. But I guess I can sit down. Yeah, thank you. I don't know why I can't log into my email. 5 points plus. Please wait. Ooh. Ready, go. Tell us about yourself. I haven't used this one before. All right. So we're going to do the purpose of the lab. Focus. This is one of the older ones. All right. So what you want to do is you're going to read your lab, explain why the lab is important and what you should learn from each section of the lab. So that's your purpose statement. So you should all have a section that just says purpose and write your purpose. And to be clear, this is going to be on a separate piece of paper. Okay? It's not in your lab notebook. Questions. List all the main big picture questions from the lab experiment. So any questions in the experiment that are generated about, like in this experiment, what would be a big picture question? So what is, what did anyone come up with a big picture question that they want to check out or share from this lab? Tell me what you put down. What? Volume of a penny. What's the volume of a penny? Or how to calculate the volume of a object that doesn't have an oblique shape, basically, right? Calculating the density of an object. So those are the whole point of doing it. I'm learning how to calculate the density of an object, or I'm learning how to measure the volume of an object. Okay, so those are your larger questions. List any and all safety precautions listed in the lab, so that just comes from your lab listing. List any and all procedures for proper hazardous waste disposal, not very relevant for this one. And then that's it. That's your pre-lab. So the whole point of the lab, and this is something that I never asked people to actually do in previous classes in 121, but I wanted them to do this responsibly, was to know why they're doing the lab. If you know why you're doing the lab, you know what you're after in what you're there to learn to do. So when I ask you, why are you doing this lab? What are you learning? You should be able to say that right off the top of your head before you get in that lab room. Okay? If you had any issue with this pre-lab, talk to me about it. I'll be lenient on this one because it's your first one, and I think, people have issues with the first one typically. So that's all there is to that. Okay? All right. Very good. All right. And I wanted to look at, hold on. I wanted to look at this too. Is the actual, does anyone have their, oh here, I have this. I have it. So thinking scientifically. So you're going to have to write two different hypotheses that explains your conclusions about your penny samples. So I want you to be able to write hypothesis and understand what that means. Has anyone tried that out or considered what it would be like to write a hypothesis for this lab yet? No? Okay. So you're going to calculate the density of the pennies, and then you're going to actually look them up in a book and see what the actual density is of copper. And you're going to have to come up with some sort of conclusion or some hypothesis about why that's so. And when you compare your results to other results, you're going to have to generate some sort of idea. So that's what you're there for. That's what you're going to, one of the things you're going to discover is that, okay? So you want to be able to ask, you want to be able to generate that hypothesis here. Right, two different hypotheses, either of which can explain your conclusions about the sample of pennies. In other words, come up with two possible causes for your findings. So remember that the hypothesis needs to be testable. Okay? So you want it, when you suggest your hypothesis, make sure you can back it with how you would test that. And you may have just tested it. So that was one experiment. Okay? You can say, well, if I do this experiment 5 times, it's going to be the same way. You know, if I got more pennies from somewhere else and I did it. Okay? So that's the kind of thing you're looking to do. All right? Did everyone read this yet? Does everyone feel good? Because it seems like people don't know what I'm talking about. But I'm going to give a little bit of time before we have labs so that you have more time to review and be ready to go. That was that. All right, so that's hypothesis, theory, scientific method. Any questions on that? All right. Now to see if you really get it. I ask you, and I want you to come up with one. Come up with any question. Consider what experiment you would make to do it, and generate your hypothesis, and share it with somebody. So you're going to come up with the steps. Let me bring those steps up again. I'm going to use this. You're going to use the scientific method. Hypothesis and experiment. So you're going to make an observation, come up with a hypothesis, and come up with an experiment about any problem or question you have. So let me give you an example of what I'm looking for. You can do this with anything. Let's say your question is how can I be certain to pass this class with a 3.0 or above? To be certain, okay? And you have a hypothesis that says if I guarantee that I put at least 5 hours of study a week in 1.5 hour blocks, or 1 hour blocks, 5 times a week, spread out so the information is fresh in my mind, I will be sure to retain all the information and get my grade. Let's just say that's a step. That's my hypothesis. And the experiment is, well, I'm going to go ahead and track, I'm going to create a schedule, and I'm going to sign in and sign out, and I'm going to track my attention. And I will study, and if I think I need more time after the first week, I'm going to add more time. If I think I need less time and I'm sufficiently studied, I'm going to reduce the amount. And I will end up with the ideal amount of study for this class that assures you get a B. So basically, you're just going to track the data. You're going to track how much time, and you're going to set a certain time amount of study. You're going to do it, and then you're going to check your data. And after the first exam, you're going to review. So based on the first exam, after you've accomplished what you agreed you would do and followed your experiment, you get to reevaluate. That's going around to the new observations. So you make your observations. How did I do? Okay, I got lower than 90 on my exam. That means I need to add tutoring because I did everything, right? So now I'm going to say I need to do 5 hours a week plus 2 hours of tutoring a week, and that will make the difference. That's your second round. And you go to your second exam and you evaluate, and you still didn't make it. Okay, I need 5 hours a week, 2 hours of tutoring, and I need to watch YouTube videos on all, and I have to watch YouTube videos on anything that I didn't understand. Okay, because I noticed there were some things I didn't understand, and I just let them go, and I never figured it out. So you see what I'm saying? So you're just, it's like you're using your own class as an experiment. And it could be anything. I want to know how to build a car, and you just, that's your question. So your hypothesis is, oh, I could learn how to build, or I need to learn how to build a car in like a week. I don't know. Whatever. It could be anything. I want to be a better husband. It could be anything, and you can still use a scientific method. I actually recommend the scientific method for these things. Because they're trackable, they're accountable, and you can actually see if it's working for you. It's not a bad thing to do. So go ahead and give it a shot. Come up with one thing, each person, work it out, and then share it with each other. And I want the other person to be like the questioner. Well, how would you control that? Well, how would you control that? How would that work? And really ask them how they can actually get there and pose more questions, okay? Do you know what I mean? How about we do one? Somebody give me an example and I'll play the other part. Give me anything. There you go. Great one. How can I increase miles per gallon? So what's your hypothesis? Okay. So now my first questions come up. Well, how much use are you going to do of your car? Are you going to set some sort of amount of miles? Okay, so that's a variable, right? He's going to control one variable. He's going to say, I'm going to do this test based on 500 miles of driving. Is it going to be winter, summer? What conditions? Okay. And what kind of car? What are the specifics of the car? What size of engine? A V6. So now you've limited the experiment to a V6 car, right? But he could do more. He could do you could do V6 and, a 4-cylinder and a 6-cylinder. You could do 3 different cars all by one. What brand of car? What maker? Mitsubishi. Okay, so you see how the questions I'm asking? Because his data would be meaningless without all that information. It would just be some random idea that someone had that nobody can use. So you have to get specific. You have to ask good questions and set up the experiment well. Okay? Now, it doesn't have to be perfect. I want you to see what comes up for you when you think about that experiment. What questions do you ask that person? What variables do they need to be considering to control? Okay? Go for it. That was a great example of something to do a hypothesis on. I would do something that you really want. Distinctions. Qualitative versus quantitative. The mass of a substance is 3.42 grams. It's a quantitative observation. The person's height is 5 feet 6 inches. It's a quantitative observation. The person is tall is a qualitative observation. The person's short is qualitative. That person was really fast, qualitative. That runner ran 20 miles per hour for 30 minutes. That's quantitative. Okay? Let's hear a couple examples of distinctions with qualitative and quantitative. What's your name back there in the purple? Stephanie. Give me one of each. Qualitative and quantitative.
Qualitative would be maybe someone's hair color, and quantitative would be their age.
Yes, excellent. Good. One more. Name, Rich. Reese. Okay, good. All right, scientific notation. Who's ever written in scientific notation here? I think I've already asked people this. All right, so scientific notation, because we're dealing with such huge numbers and such small numbers, we need to have a way to express it. So, so when you have number, like, let's just see what we got here. So 59,400,000 scientific notation. So you're going to basically change it so that it expresses the number in a power of 10. which means I want to why does that happen? One moment. Sometimes this is difficult. That's why I don't like using this thing all the time. Darn it. There we go. Okay. So we're going to change it to a power 10, right? Because I can say, when I look at this number right here, I'm going to just use the number 100. Okay? So I could write 100 like this. 1 times 100, can't I? And that's 100. Same value, isn't it? But I just wrote it differently. I could also write it like this. 1 times 10 times 10. Isn't that 100 also? Now, what I can also write it like this. 1 times 10 squared. Isn't that 100? So, that is what scientific notation is all about. It's taking these big numbers and using a simplified way to write them using the power of 10. So, if you look at this number, 59,400,000, I can say that is some number times 10 to some power, right? I don't know what that is off the bat. I have to actually look at it. Do you have a question? Probably. 6, 7, yeah. So you know what you're doing. Good. All right, so let's look at... let's just look at a couple of these numbers. So that's 100, right? I'm just going to do a couple more. 1,000 would be 1 times 10 cubed. Because 10 cubed is 10 times 10 times 10. That's 1,000, right? 10,000 would be 1 times 10 to the 4th. One times 10 to the 5th is going to be 100,000. And so on. 1 times 10 to the 6th is 1 million. And it keeps going. All right? So that's the simplest version of scientific notation, just using 1. Now, I could look at this number, this 59,400,000 number, and I will just put the decimal now right in front of the first whole number, 5. And when I put the decimal in front of that, now I have a different number. The number I have right now is, let me just get rid of this. Is 5.94, and the rest are zeros. So I'm going to take the decimal. Now, where was the decimal originally? It's not shown, but it was here, wasn't it? As far as the value of the number. So the decimal was there. I'm going to move it all the way over here, right in front of the first whole number, so that I can have some number that looks like this. So that I have one whole number, and then a decimal, and whatever other numbers were there. Okay? So in this number, it just happens to be that there's only 3 whole numbers. The rest are zeros. So those are the ones I write, 5.94. Okay? Everyone with me? Then I'm going to multiply it by a factor of 10. Times 10. 10 to the what is the question? Very similar to how we just did the other ones. 100 is 10 squared. We're going to look at how many zeros, like how many thousands we have to multiply this by, right? Or how many hundreds we have to multiply this by. Or how many factors of 10 we have to multiply this by to get this number. So the point is that this number right here that we come up with should equal this number. The value should be the same. You are not changing the value of this number. You are just writing it differently. I'm going to say that again. You are not changing the value of this number. You are just writing it differently. And that is the test for yourself in the future. People make mistakes on this over and over because they change the value. They think they could just move the decimal place. Was it this class where I said if you move the decimal place, it's like, $100 or whatever? You give me $100, I give you $1 back? Did you remember that? No, you didn't? It's the same thing. It's like if I say, what was your name again? Stephanie. Stephanie, I want you to give me $100 and I'm going to pay you back, okay? In 5 minutes. You give me $100 and I give you $1 back. That's what changing, I just moved the decimal over 2 places, that's all. Right? I said it was $100 and I gave her 1. I just moved the decimal over 1 place. But people do that. In chemistry, they move the decimal and they think they could just change the value. You can't. Consider it money. Don't move the decimal place unless you're representing it properly. This has to be 1 times 10 squared to be the exact same value. You see? If I said this was 1 times 10 to the minus 1, now I have 0.1. Now I have really short change. I gave you a dime back. Okay? So over here we got to figure out how many decimals to move, how many powers of 10 to multiply by to keep the value. And the way you do it is you just count. Just count zeros from the original location. The original location was here, so we're going to go 1, 2, 3, 4, 5, 6, 7. All the way over to there. So times 10 to the 7th. So 5.94 times 10 to the 7th is how to write that in scientific notation. Okay? Now, when you look at this number, don't look at it like it's some other language. It's just a mathematical function. This is this. This is the same thing as saying 5.94 times 10 times 10 times 10 times 10 times 10. 1, 2, 3, 4, 5 times 10 times 10. Okay? It's the same thing. So if I actually multiplied all that out in my calculator, I should get this. Which is that. Same answer. So I know I'm right. Remember I said you know you're right in this class? You know you're right. Because I can check it. 5.94 times 10 to the 7th equals 59,400,000. It makes sense, doesn't it? If you're going to multiply a small number like 5.94 times a number like this, 10 to the 7th power, it better be big. Okay? It's going to be huge. And that makes sense. So it makes sense. So I'm trying to teach you how to look at things logically so that you know they're correct. Okay? Make sense? Good. Whoops. We're just going to go over that. All right. Now, if you had a negative, all right, these are kind of rules. Now, all right, we'll do the rules just because the rules are kind of fun. So the exponent is equal to the number of places to the decimal point is moved, basically. The exponent is equal to the number of places the decimal point is moved. The sign on the exponent indicates the direction the decimal point was moved. So in that case, we had this 59,400,000, right? We moved it from here all the way over here, 7 places to the left. 7 to the left. So if you moved it to the left, it's going to be a positive exponent. If you move it to the right, it's going to be a negative exponent. And in this case, over here, the 0.003435, we're going to move it to the right 4 places. That means it's 3.50 times 10 to the what? Minus 4. Because I moved it 4 places. So now if you're the kind of person who wants to memorize these kind of things and use them but not understand them, that's fine. But I really encourage you to understand it as a value. Understand the number as a value when you're doing it. If you have this 0.00350, that's a small number, isn't it? And if you're going to multiply that by 10 to the minus 4, does anyone know what 10 to the minus 4 looks like? It's like this. 1 over 10 times 10 times 10 times 10. It's actually 1 over 10 to the 4th. It's the same thing. So 1 over 1 is 1. This is 1 over 10,000. So it's 1/10,000th. Right? So that's tiny. That's small. So your number, if you have a minus exponent, your original number should be really small. And you can always write it out. So when you have this 3.5 times 10 to the minus 4, I'm going to go ahead and I do it this way. I don't memorize the left-right thing. I just say, oh, minus 4, I'm going to move it to the left 4 places to see what the actual value is. So I'll move it to the left 4 places, and I get this. And that's the same number, so I know I'm right. Okay? Same thing with the right one. If it's 5.94 times 10 to the 7th, I'm just going to move it to the right 7 places, and I should have the same number. Okay? So either way you want to do it, I'm going to give you access to all these PowerPoints so you can look at that or write those rules down and remember. Because the problem with this rule is this is based on starting with, you have to remember that this is based on starting with a number that's not in scientific notation. There will be times where you have other situations and you're like, which way do I move you're going to be moving this decimal place all over the place. Trust me. And I'm going to show you a couple different examples when you have to move them. So you want to make sure you do it right. All right. All right, so here's some practice. So which one is this one? A, B, C, or D? So we're going, whoops. Wow, that really is not the right place. That's weird. All right, we're going over 1, 2, 3, 4, 5, 6, 7, 8, right? 8 places. So it's going to be this one. Good. Five to 7. All right, we're going to stop. We have a lab at 7 what? Oh, no, we're not going to stop. I have 5 more minutes. 10 minutes is good. All right, sorry. I thought it was... all right, let's do this because this is important also. All right, so now when you make a measurement, this is good. When you make a measurement, I'm going to use a different scale here. I'm going to say that I have a ruler. And the ruler has 1 inch, 2 inch, and 3 inch. If I measure something, and it falls right here, let's say that's my, whoops. Let's say that I measured it, right? And this is where it came across the line right here, right at this point. Okay? That's not a 1. So I measured it right to that point. What do you think the answer would be if you were to report that measurement? What would you say it's about? 1.4? Okay, good. Now, let's look at this situation. It is absolutely certain that it is 1 point something, isn't it? You are absolutely certain that it's 1. Because it's between 1 and 2. And 1 and 2 are marked on the calibrated ruler. So this is a certain number. Now what about the 0.4? Is it certain? No, it's totally up to your interpretation. And every person that reads this ruler might say something different. Someone might say 1.3 there. Or someone might say 1.5. Okay? Maybe not. But it's up to interpretation. So this number is called uncertain. In science, when you're doing experiments and you do a measurement, you always measure to one uncertain number. So in this case, you would answer 1.4 as you thought. That is correct. That is a correct and accurate way to measure this. So the answer is 1.4 here. Now, what if it landed right on the 2? Now what would my answer be? It would be 2.0, and that O means something. That O is saying that the uncertain place is on 0. So you report always to that 0, that uncertain place. Okay? So when you do your measurements in lab, you will always take one further. So you look at your scale, like a typical centimeter scale on a regular ruler will go out to point. It'll be based on centimeters, right? So it goes. You have your. There might be millimeters in there. So if you have millimeters, you're going to end up reporting 0.00. You're going to go out to the 100th place. Okay? So that's that. So now let's look at this. So therefore, you can say that this ruler measures to plus or minus 0.1, whatever the units are. Okay? Because the decimal place here is the uncertain one. The 10th place is the uncertain digit. All right. Now this temperature, this thermometer here, is measured out to here. Right there is where it measures, right? Now what is the gradient of the thermometer? How is it broken up into? It's 20 here. Then you got a line here. That must be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So it's broken up into 1 degrees, right? Degree by degree. So this is certainly what? At least 21, right? And now where's the uncertainty? In the 2, right? So it's 21.2. So you would report that 0.2. You would not report 0.20 because that is 2 uncertain numbers. So you only report 1 uncertain number. This is a no. You do not do that. Okay? So therefore, this thermometer reads to the accuracy of plus or minus 0.1 degrees Celsius. Because it can be, the uncertain could be plus or minus 0.1. Okay? So when you measure, you're going to measure that way. I'm not going to do sig figs. Not yet. I want to do this. The metric system. When we measure, we are going to be using the metric system. These I want you to memorize. You have to know these prefixes. Giga, mega, kilo, hecta, deca, deci, centi, milli, micro, nano. And basically all these are exponents of 10. Each one represents an exponent of 10. So when you see something like kilometer, that means kilo. 10 to the third. So all that means when you see kilometer is that kilo is represented instead of a number. Kilo means a number. The number that kilo means is 10 to the third. So that means 10 to the third meters. You see? Kilometer is 10 to the third meters. 10 to the third is 1,000. Therefore, there are 1,000 meters in a kilometer. Right? Very familiar, right? Centimeter. Centi means 10 to the minus 2. Therefore, a centimeter is 10 to the minus 2 meters. 1 centimeter equals 10 to the minus 2 meters. And so on and so forth. Millimeter is 10 to the minus 3 meters. So you have equations now and equalities that you can use in calculations. You can convert from millimeters to meters or meters to millimeters. And I'll show you how to do that more in the next class. But I wanted you to get started on learning these. You are responsible to know these, okay? They're not that difficult to remember. Giga is already in your language probably if you have a computer. Mega should be too. Kilo is not as common, but it's pretty. These two are not very common, hecto and deca. But then deci, centi, milli, micro, and nano. Don't worry about femto. What's that?
Where you're from?
Yeah.
Those 3 not really nothing. Those further down.
Which ones are familiar in Africa? Oh, yeah. Yeah, right. Hectares and stuff like that. Yeah. Okay, so there you go. Yeah. Pico de gallo. That way you can remember that one. Nano. technologies. Remember nano view? What was the nanoscopic? Nanoscopic, 10 to the minus 9th. Done. Micro, 10 to the minus 6th. And check out this symbol. You got to know the symbol too. This is the hardest one right here, is the micro. It's a mu. Okay? So you want to be able to notice if it says, if you have a micrometer, that's 10 to the minus 6 meters. Okay? If you have a decameter, it says damn. Decameter. My pen doesn't. This computer's freaking out. I'm writing in one spot and it's coming out on the other spot, so I'm just going to stop. All right. Let's stop here. Thank you for your attention, and I'll see you in lab. Yes.